Then it says preparing. All right, it looks like we're live. Welcome everyone to another lesson of C++ London University, where we're talking about C++ standard library today. My name is Alex Voronov, and I'm doing this course on standard library. And this one is going to be the last lesson. We'll wrap up. I'll cover a few things which we haven't touched in the previous lesson, and most of the lesson I'm going to focus on the massive homework which I gave the last time. As some of you may know, like we are live streaming both on YouTube and in Zoom. And in order to get to Zoom, first you need to get on Slack. There is a C++ community on Slack, and our university has a channel there, and like we post announcement there, we post detail there, we discuss lessons, problems, and so on. And you can also ask for advice. And if you want to join Zoom stream and be able to ask question in person, please follow there and find the details how to join. And yeah, just even outside of this lesson, always welcome on Slack if you have any questions and want to learn more about C++. And also you can explore there, and there are conference channels or just #learn channel where you can ask questions for a broader audience. So welcome on Slack. And this is the structure of the course, and we are on the last line, which changed from what I promised the last time. And basically, I took a look at the what it was in my first lesson, and it seems quite close, but a few things changed. And what we've done is we started talking about algorithms earlier, and therefore the problems which we can approach became, I think, more exciting, and still caught up on the most important things about most important containers. And for today, I just decided that I want to explain the exercise which I provided last time. And there are a few interesting subjects which emerged while I was going through the exercise. And this gives me an opportunity to most importantly to talk about std function and how it can be useful when you are writing code. And also I want to mention such a thing as structured bindings, which is quite nice when you're working with standard containers and pairs and so on. And it makes things more like more readable. And a few more things about algorithms. Just a second. Tristan, you're saying that YouTube stream haven't started. I think it looks all right on my side. Yeah, it looks like we are going. Just refreshing the page helped me. Please let me know if it's not correct. So far, I'm gonna proceed. And with a quick recap of what we were doing last time. And last time, not the last time, but for all the lessons in general, we are writing a lot of unit tests, and we are using unit tests a lot. And in order to write unit tests, I suggested a framework, Catch2, written by, like, originally developed by Phil Nash, which is very convenient from the point that you can download only in single file, put it in the folder of your project, and include it, and then use straight away. And I will just again point in the places where it's being used. The syntax is pretty simple for the things which we need it for. and it's better than std out because we can programmatically validate that our expectation is still correct and don't need to eyeball it every time we run the program. And still like very easy to start. So I encourage you to go to the project page, grab the file, and start using it in your explorations. And last time we were talking about using custom types in maps sets and their unordered versions, and we were talking about their underlying data structures and therefore requirements imposed by these data structures. And this is an example of the code which is not going to compile because the date is too simple to be used as a key. And we were discussing what are the requirements and how to implement in the code so it compiles. And we even written our own hash functions, which was quite exciting. And as a home exercise, I was suggesting to grab a English language dictionary and to grab English language dictionary and see what kind of exciting anagrams we can find there, and see if we can like what's the word with most anagrams to it, and also what are the longest anagrams. And this was a template of a test which I suggested to use, and I'm gonna like also remind what were the types which I was using. Is just basically for testing convenience, and the key thing which needed to be populated is this word set after passing. It's basically a set of word sets, and after passing the dictionary, I was suggesting to fill the word sets for the words like with most anagrams to it. If there are more than one, then more than one set, and same for the longest anagrams. And here I'm going to give you the answer, and that's the answer which I found. So the largest anagram set, and apparently there is only one, has 15 anagrams, and it's like alert, alters, arters, astral, luster. I'm not going to finish it, but yeah, not the most useful knowledge in the world, but still quite fun. And I would say the result for the longest anagram I find a bit underwhelming because it is just shuffling entire words rather than letters. And looks like something chemical in all three cases, although we know that the length is 22 and there are three pairs of such words, at least in the dictionary which we looked into. But it's not like the most important knowledge in the universe. On the other hand, for example, if you did the exercise, now you know how to process a dictionary, and you can implement some more interesting queries about the properties of the words if you are interested. And in general, like you know how to work with larger data sets. And that's what's more important about this exercise, rather than just knowing 14 anagrams to the word alert. And basically, because it's not an exercise which fits into one screen, like the solution for it, I'm gonna go through the solution and explain the functions and the data structures which I used for my solution. And also, I used a few things which are not required, but just to make things a bit tidier, and you may find them useful. And I will explain a few new bits here today. And that's the plan for the lesson. So before we proceed, I suggested that people send me their solutions. There were two brave people who sent their solution, and John's solution was correct and also quite efficient. I played a bit with benchmarking. I didn't bring the results, but it's around like 10% slower than mine, which is pretty good, which puts it into the same ballpark. And Eugene also sent his solution, and he was really close. And he'll probably be able to spot one thing he has missed. But it was also like well implemented, and just one small missing thing. Because I didn't tell you what's the answer is expected, it's hard to validate, and therefore good job for trying. And I hope more people tried it for themselves, just decided not to share. And you can check if your solution looks close. I also can't be 100% sure that my solution is correct, and therefore if you have better anagram sets, please share, and please show me how I was wrong. It's completely possible. And I'll post an update in this case if I did something wrong. All right, that's it for the introduction. Sorry, and if anyone has any questions so far before we proceed into details, this would be a good time. All right. I also, just for the plan of the lesson, it's basically going to be mostly going through the exercise, and the subjects which we're going to touch is a few algorithms, STD function, and structured bindings. I don't have any practice exercises today, and obviously there are going to be no homework because it's the last lesson. So we may finish a bit earlier. Depends on how many questions do we have on the way, and questions are welcome. We, as usual, gonna, like in the middle, we're gonna have a short break probably for 5 minutes, because it's nice to stand up and stretch a bit and get some air in your lungs. So we're not sitting for 2 hours straight because it's already evening, and it's quite boring stuff. So a little bit of stretch and break will be nice. And with all these announcements, now I'm going to proceed. As I already showed, first I'm going to quickly talk about the way I read the file. And I don't want to like dwell much on it. It's just in case people had problems or found it difficult, I will suggest this solution to use. The path to the file doesn't matter. You can change it. You can put it somewhere else on your computer. But basically, that's enough. I used input stream and getLine function, and just as long as stream is in good condition, therefore it's not end of stream, I was consuming a line and putting it. And this is a small test which I suggested just to make sure that your word set is looking the same as mine, or at least close to it. You can see like you got the same number of words and the start and the end validation. And one thing I wanted to share is when basically I have like a vector of values, especially when it's an extensive vector, is how I do more detailed validation. And this is the test for the same function with more details. And just what I wanted to show is these 3 functions: all off, none off, and any off. This any off example is a bit made up, although all off and none off cases are pretty important checks in this case, which allow me to quickly see some additional properties of my data set, and just make sure that yes, I read everything correctly, and my input is a good input for the exercise. And what I'm doing here is I'm reading my words into a vector, make sure that it's not empty. It's not necessary for these algorithms. And then I use the checks, and what this thing does is all of it takes a container, a range with by begin and end, and also a predicate. Predicate is a function which takes some object as an input and tells yes or no, and therefore like it needs to return boolean. And in this case the element, the object have to have the type string, and in this case I also use this all of for each character in this case. And I'm checking that it's lowercase, and we already discussed this when we were doing palindromes, and it's a letter, and by this way I'm validating that all my words have nothing but letters, and all of the letters are lowercase. And when I do this check, it's like I'm confident in this property. And these functions are their replacement like for each element in the container. If the property is correct, keep going. Otherwise, otherwise return false. And is just shorter, and also quickly tells me an intention. For example, between all of and any of. In this case, I clearly see that that's requirement for all the elements, and this just comes from the name of the function, from the name of the algorithm. And in case of any of, I'm just making sure that there is at least one element which satisfies the predicate. And in this case, because the data set is quite big, I thought that it's going to be reasonable to look for words which start with key. And yeah, there are such words. And before I check this, I also decided that I can check that none of the words are empty, which means I probably like either the file is not in the best shape, or maybe I read something incorrectly, and therefore I put a require here because in this case, if if there is an empty word, getting dot front would be undefined behavior, and that's the structure of this test. And also I will just take an opportunity to remind the difference between require and check. And in case of require, if the condition is not satisfied, in this case, the test stops the execution, and the further lines of the test are not executed. In case when check condition fails, it will print the error, but the test will continue going, and therefore may produce more errors if we want to validate more properties. But if something is a hard requirement for the subsequent for the following code, is just like it should be require rather than check. And test case is how we it's basically it's a small function which is doing one piece of validation. That's unit testing. Any questions so far? Lauren was asking about streams, and if there is connection to a database, can we use fstream to import from it? It depends. I would say not standard library. Like standard library is not aware of the databases. On the other hand, you can implement a streaming object which would allow you to read from the database, but it will be it will have to be your custom type or some third-party library in this case. And there is a question why unsigned char rather than not int for lowercase. The elements in the string are unsigned char, and that's why I decided to keep it like this. Practically, it doesn't matter. because we are operating here with only English language characters, and therefore it doesn't make a difference. If it was something about encodings and so on, I would be more thoughtful of it and just have additional tests. But just for sake of simplicity, I used the same thing, which is used in the string. I'm not sure if it's signed or unsigned, but all the interesting characters are in the part which is the same for signed and unsigned, and just to avoid anything with a sign change for the character, I used unsigned, so it doesn't make significant difference here. But yeah, a good question, and in real world code, you may want to pay attention to it. Although still, std string, as I mentioned before, doesn't have any knowledge of Unicode. It's just basically a vector of characters, and like 8-bit characters, and there is also a wide string for 16-bit characters. But it's just kind of byte by byte, and has no knowledge of actual like symbols, or I don't know what's the correct word for the Unicode things. We'll just, whatever you put there, you'll find it there, and it's going to be no smart transformation and so on. There is conversation about adding Unicode support and just Unicode awareness to the standard library, but it's not there yet, and there is some hope for C++ 23. It's still 3 years away. All right, this was the main use for all of, none of, and any of. And I'd also like to show a small edge case where like we are checking the empty container. It's just important to kind of keep this in mind that on empty container, if you're asking if all of the elements of an empty container are satisfying the predicate, yes, all of, like if there is no elements, then all of them kind of satisfies the predicate. Same goes with none of, and if you're asking, is any element in the container satisfying the predicate? The answer is no when the container is empty. And I used vector as an illustration, but any other containers, set, map, and as I already showed, string would work here, as long as it supports forward iteration. Any question about these 3 nice helper functions, helper algorithms? Let's move further then, and now we are onto the main problem itself. And before we dive into code, I would like to discuss our strategy, and then start looking how our strategy looks. How is our strategy in the code? And that's my plan. How I'm gonna approach this. For the solutions I received, it was quite similar, and yeah, I haven't seen any other ways to approach it. I can imagine those, but though they may be less efficient, and therefore here is the suggested approach. So first, we will, and that's probably the trickiest part. We're gonna organize. We're gonna extract anagram sets from the dictionary. Anagram set is the set of words, all of which are mutual anagrams, like in a single set. And those are our objects of interest. Then we want to see the largest set and also set of largest words. And then we gonna do pretty similar thing for in order to get our two answers, we're going to go through all the anagram sets and first see what's the largest size there, and then we'll filter out all the anagram sets with the same property of size. And we could do it on the same iteration, but we're going to do it on a separate iteration, as we're going to also look through the anagram sets with like for the longest word, and then we'll filter out all the sets with the longest word. And then we'll just need to compose our answer. And still, while we're talking about code structure and just our solution structure, that's how it's going to look in code. I've given some definitions, and then for in the following slides, I'm going to talk about the implementation. And as I said, first we're going to get the anagram sets, which is going to return us a vector of this set. It takes the words as input and returns only the sets. And then I'm going to scan this set for longest anagrams, and then scan this set for anagram with most words. And the return value in this case is set of sets, because there can be more than one. As you already seen, there is more than one set of longest anagrams. And when I have these functions, the function to find anagrams itself look quite simple. I just get the sets and already can compose my answer. And are there any questions here? I'm gonna proceed now, and this is like we're gonna go through this list during this lesson. And first, we're going to start with collecting all the anagram sets into the dictionary, and that's the way I did it. There are a few interesting bits which I've done here. And I'm gonna talk about them later. And the first one is just I don't think we've talked about I don't think we have discussed the sorting before, and also this is just like a nice improvement over the syntax, and I'm gonna discuss this too. There is a question on the stream: if are we talking about std span? Not in this lesson. And back to collecting the anagram sets. Yeah, so one property which is important to notice, and which we use, is that basically, if I alphabetically sort the letters in words for mutual anagrams, the sorted letter vectors or strings, they will be identical, and that's probably the most efficient way to compare them. Another one could be using something like unordered multisets, but their composition is yeah, like it's going to be pretty close, because their composition is linear, and then their comparison is also going to be linear. These are two options, and then I organize. I kind of group my words by. I use this sorted letter string as a key, and if to basically then I put all the words which transform into this sorted string as into a vector, and this makes me in the end this makes me an anagram set, and the only thing I need to do is then go through this map and see if there is more than one word, which means that there are anagrams to this word, I'm returning this. I'm returning this as a set, as a part of the answer. Any questions about these bits? John is pointing out that std set of word set will be, it's a question, will it be faster to search than word set? It will be faster to search, yes, but we are not searching it yet. You'll see what I'm doing next, because my goal is to iterate over it. And in general, unless you have a reason, the guidance is prefer vector, because it gives better cache coherence, and in general, it doesn't tell anything like additional. And for in certain cases, I've chosen sets just because they are unambiguous and easier to compare for our purpose. In this case, there is no reason to choose anything else, and vector does all right. The set would do the same, because the only thing we need to do with this answer is to, like in my further code, is to iterate over it. There is also a question about using emplace hint and std move for composing the sets, and we haven't covered std move, and it doesn't seem critical here, but yes, it could be beneficial. And because we're not using the words anywhere else, that's correct. About emplace hint, I'm not sure, because in this case it's just a vector, and the operation is pretty cheap here. And yes, like if we were passing, for example, the words, still we use them only once, and therefore the question about std move is correct. But also we just were not covering this in this course, and it's like I would count as a minor concern. So no problem. And but from the point of more efficiently inserting, I'm not sure that it's helped, because in general we compose in the set only once. A few words about sorting. What I wanted to show here is the basic use of sort, and then how you can change the sort ordering, even doing some crazy things. And the example is quite simple, but still gives some idea. Also, one thing which I not often use in my unit test example is section. And the way section works is all sections run independently, and they don't overlap. Therefore, the code will go, the numbers will be available for the section, but basically my code will enter the first section, and then test execution will exit here, then skip the first section, enter the second section, and exit here, and same with the third section. Yeah, so we can consider them independently, still having them kind of as a part of the same piece of code. And in the first case, I just get my numbers and sort them with default comparison operator less. Operator less is the only requirement from the sort. There are some also requirement that the object needs to be either copyable or movable. I don't remember. I wonder if Tristan can help me with this. In our case with the integer is no problem. It is no problem. And yeah, that's the way it works. That's the input, and that's our output. If we want to change the sorting order or the sorting function, we need to provide a comparison function for compare less, and we've done quite a lot of like we talked about it quite a lot in the previous lesson when we were talking about custom keys uh, for maps, and the thing which we need to pass here, the uh, a binary predicate for compare less, to be precise, is the same, and it's kind of compare less, but we intentionally make it greater than, and in this case, what happens is that uh, we basically reverse the order, because we are returning true for less when actual elements are greater, and this just inverted the order of sorting. Another way to do this, which you may guess, would be to use the same comparison but reverse iterators. And it may be slightly slower, but first, you need to measure. And a general note on sorting: the complexity is O of n logarithm n. Therefore, the basically it grows a little bit faster than linear with the size of your vector, but not that fast. And here is an example, just so that it can be like anything. This is a function which I additionally implemented, but it didn't fit the screen, and what it's basically doing is counting the sum of digits, and you can see that this number has the lowest one, and then like 6, 7, and so on and so on. And still, whatever sorting order you are interested, you can use that, or you can compare by particular. If you have a class, you can compare by particular members of this class, and so on. That's sorting. Eugene is asking about what was the thing with square brackets for the 4-range loop, and I'm going to get to it in a few slides. Oh, John is making a good comment, which I missed, that standard library compare functions, std greater and angle brackets, or std less, is a great thing here. And yes, I will make a note for the next time. This is a good suggestion. So there is a bunch of functions like std less, std greater, which you could pass here as a parameter, and you don't need to type this code, for example. And it's a good shout. It's probably from it probably appeared in Connor Hoekstra's talk, and yeah, because it's already there, you should avoid writing the code. It's a good correction. Thank you, John. And Tristan had a comment that the requirement for the class probably to be just move assignable. And if it's move assignable, it should be okay to sort then. And another interesting thing about sorting is basically when elements are equal, and I won't be able to form a test for it because the test is going to be undeterministic. If the elements compare equal, which means neither less nor less when they are swapped, the order is not guaranteed. And if we want to keep the order from your original input container, there is a special function called stable sort, which from the point of algorithmic complexity has the same complexity, maybe a little bit more overhead, but it has a property which we can rely on. And here I compare by the last digit and order by the value of the last digit, like 5, 6, 6, 9, 7, 9, 1. And you can see that relative order between the elements, for example, like 76 and 26 by my comparison function will compare the same, but they are guaranteed to keep the same order in case of the stable sort. And one real world example where I can see stable sorting operation is file managers. And for example, when I'm sorting by extension and then by date, it tends to keep oh, sorry, first by date and then by extension, it tends to keep the date order, and therefore it looks like file managers are using, at least good file managers are using stable sort for these operations. Therefore, when I'm arranging the elements which are not always deterministically orderable, it remembers my previous sorting and respects it. And if you need to implement something similar, there is just a simple algorithm for you, and you need to understand all the details how it works. Any questions? Any more questions about sorting? And then I'm gonna get to this nice square bracket thing, and it's called structured bindings, and it's not immediately really. It has nothing to do with standard library or algorithms or something. It's just a thing which I often use instead of getting it like a name like a group and then using dot first and dot second because they are not descriptive enough. And here I can clearly call it a key for the set. It's not just dot second, but it's a word set, and therefore you can imagine that here it would be it could have been group dot second and it localizes the meaning better. And Lorraine is calling out it's similar to unpacking in Python. I think yes, that was the inspiration. Although C++ has, in terms of type system, has more constraints, and therefore not always where you can use unpacking in Python. You like in similar positions, you will be able to use. You will be able to use structured bindings in C++. And I'm going to give more examples of this. And first, this is a piece of code from the previous lesson. And it's just remember a simple class date, which has year, month, and day. And we were putting this into multi-map. There are a few bits about this code where structured bindings may come handy. Here it's just a bit more artificial, but an example that you remember that an element of multi-map is a pair with dot first and dot second. That's how we access the pair in the beginning of multi-map, which has date, this date, and the word unit testing. And because it's a first class, I call it first class date. Yeah, that's how I capture it by reference. So here I basically created two references, one for the dot first, another one for dot second, and I can split it in even further. And here it's collecting it by value, and therefore it doesn't necessarily needs to be const, but because I wasn't not modifying it, and here I can access it by immediately by the name like year and month. Rather than doing something like classes.begin.first.year. Yeah, this is one example. And what's interesting, you can also use it with arrays, but only basically The simple explanation will be that arrays which size is known upfront, and this works with simple arrays and also with std arrays, because they also have provided the type compile time, and it's also somewhat similar to Python unpacking in this case, as you can see. And in the second example, I show even how can I modify the value, and yeah, that's I never actually had in practice an example where I needed to use it with arrays, but very often it comes very often with something which is looking like an aggregate type, and or which is a pair or a simple structure. And another example I have related to our multi-map is remember our equal range function, which returns the range of the elements, and then we do this dot first and dot second here, because it's two iterators, and with structured bindings I can modify it in this way, and for me it's just when it's range begin and range end, slightly easier to read for me, I would say. And I already know that these are iterators. I don't need to remember what's dot first and dot second. And therefore, usually, I already it was tempting to use it in the previous lesson, but I decided to put it into this one because when I'm operating with a pair, I would prefer to give things a name. And therefore, when I'm writing some code about this pair, it's just much easier to understand from the first place. So it doesn't make your code more efficient, faster, or something like this, but from the point of readability, and and even sometimes just less writing, it makes it much nicer. And therefore, I recommend this property when you're working with maps or with some methods and algorithms which return you a pair of values which is not named anyhow. Any questions here? Vlad has a question on YouTube, but I'm not sure I'm getting it. The question about is about reference sign, using or not using the reference sign, and basically it's just for the. It depends on what you want, and if you want to copy the values, basically use the value. If it's okay for you to bind by the reference and therefore avoid copying, I would recommend to use references, but there is no uniform. Sorry, universal answer here, and just be mindful of this thing. That's an important note, though. So it's there is no universal recommendation, and just be mindful. Can you by const reference, it usually works, and basically const reference binds for the object for the entire lifetime. Objects still can go out of scope. For example, you can clear them up, and that's going to be bad. And in any case, be mindful of the lifetime and of copying overhead, and do you want to copy it or not. And also const or non-const reference, depending on do you want to modify it or not. And yeah, that's all about first back to the solution, as we have talked about sorting, and we have talked about the structured bindings. Any questions about the getting anagrams, the function itself? And then we're going to move to the next step of after we've got the anagrams, just finding the right ones. All right then. So we are going to be talking about finding the sets with the most words and with the longest words. And as you can see, the things which we need to do are pretty similar, and they only differ in a few aspects that we are basically looking for a different property, which is like in one case we need the size of the word, in the other case we care about the size of the set. And it appeared to be a good opportunity to show std function, and therefore this may look a bit intimidating, but that's probably the most interesting and the most important bit of this lesson, which I'm going to try to explain. And here I introduce std function, which is a generic type which stores an invocable object, and in the angle brackets, like it's you can see it's a template type, and you don't need to have much knowledge of template in order to start using it, because it's also the same as with vectors. You don't need to have much knowledge of templates in order to use vectors, although vector is a templated type. Same with std function. The only thing you need to know about it is that in the angle brackets, you put the return value before the parentheses, and in the parentheses you just list with comma if necessary the types of the arguments. And that's how you, and basically in this case, this std function will be able to store an invocable object which takes these arguments, in my case word set, and returns size t. And this thing can be anything, as it can be pointed to a function, it can be a lambda, it can be a freestanding struct, in this case, which is a functor, which has operator parenthesis overloaded. And I will show these examples. As for now, getting back to the function, I created two helper functions. One is get max property value, which I pass this function, which is going to compute my property, and then I only need to figure out the maximum value. So I'm going to use max element there, and I will show you in a bit. We'll show it to you in a bit. And another one is filter anagram sets, and here I also pass a predicate, and it's quite similar, but because it's a predicate, it tells yes or no, it returns Boolean. In this case, property has the type of size t. We care about something which is either size of the word or size of the set. And when it's a predicate, we need to tell for each entry yes or no, and that's the way we do it. And then if we imagine that we have implemented these functions, our code goes this way. We pass our anagram sets, and that's my way to compute the property. I take the word set and return its size, and then that's my predicate for filtering the anagrams, and I also pass this predicate. It's a lambda again. Lambdas come pretty handy here, and filter anagram sets returns the set, and I can pass it straight through and return as a function return value. I will give the details on these functions, although if there are any questions, they will be welcome.
Yeah, does that do multiple sets? I was just wondering.
Sorry, what do you mean by multiple sets?
If you had multiple sets of the same length, same number of anagrams in a.
Yeah, the idea that I return set of sets in this case. I can first I figure out what's the maximum size of the set, and then for each like this, what this lambda does, it will when you give you when it gives the set, it will tell if the set have the expected size or not, and therefore in this magic field anagram sets function, I will for each set see if it satisfies the predicate, and if it does, I will put it into my return value.
Okay, thank you.
Let's look into details. And wait. First, I'm going to talk a bit more about std function, and I wonder if it's going to be a good time for a break before we go into so we're going to stretch a bit, and because that's going to be the new material, we just come refresh to it and continue with a bit fresher mind. So I'll suggest we take 5 minutes break and come back at 7:31 London time. 1 minute before we continue. All right, let's go. So first example about std function is I created a function which takes a function. In this case, by takes a function, I mean takes std function, which is a predicate, and it says, is this the word of interest? And it just counts words which satisfy a particular property. And my first example is counting words with lambda, which tells if the word starts with y. I already warned you before that before querying .front, you need to check that the word is not empty. And yeah, that's these are the same words as we're using in the dictionary, and just not the most useful information, but for illustration purposes, if I do count words and pass my lambda here, I get my answer. Any questions on this example? Now I will keep the signature here, but the function, you can imagine that the function stays the same. And this is an example for with just normal, usual freestanding function. I also can pass it to std function, and as it worked with lambda, it also works with a freestanding function, and also gives me the answer. Just for variance, it's for variety. Sorry, it's a different function, and you may remember this one. That's the way we were detecting the palindromes, and the a bit more advanced way to do it. I was mentioning a functor here, which is basically a structure class which has operator parenthesis overloaded, and in this case, it needs to take take the same type as an argument, and also return what is expected. And in this case, we can also pass an object of this type into, like, it will be converted into std function, and std function will store our functor and invoke it like when it itself is invoked. And what's interesting about functors and why they are useful, although they are more verbose, is that you can customize them by construction parameters. And in this case, I was able to write a functor which, when parameterized by the length of the word, can tell you if the word has given length or not. And we can see the number of words of just two letters long words, and there are more 15 letters long words in the dictionary, which I suggested for the exercise. These are all the examples I heard about std functions, and now it's a good time for questions about these small examples. And we'll go straight into what did we do for figuring out the anagrams. So this like here we are back to the piece of code which we're gonna break into smaller pieces. Lauren is asking what's the difference between lambda and functors. Lambda functions are created by lambda expressions which go with this like square brackets and so on, and functor is usually like needs to be a separate class. And I think actually like in underlying implementations, either you can imagine that lambda is a functor, or you can at least maybe it's actually the real representation. I'm not sure about the standard details, but the thing is that lambdas are harder to customize. Once it's declared, you cannot put any additional properties there. Yeah, lambda, I'm not sure about exact details, but it may generate a functor. The thing is that when you write your own functor, you can specify the constructor parameters, and therefore I showed an example that, for example, this is like the additional property which is stored here, and having written it once, I can just provide a different value in a single place, and it's gonna return me different answers. And if you try to do the same if you try to do the same by lambdas, it's going to be probably two different lambdas, and therefore a bit of code repetition. And that's the benefit of just writing custom functors. If you are not planning to reuse it, it's just usually easier to go with a lambda. Vlad is asking, did I need to explicitly delete the constructor? And I probably did not, but I prefer to be even more explicit here. It's a stylistic choice in this case. And anyway, I'm not using it in any means. It was just a stylistic choice. Same as I didn't need to declare this private, for example. Still would work. So that's the way we compute our properties in a generic way. This is like a small assort, which is just more for documentation purposes, that I shouldn't have never pass a thing which is an empty set, because then I'm invoking max element, and max element doesn't go well with an empty container. And then I have my property computation, but what max element is requiring is a binary predicate. Yeah, so it can compare one element to another and see which one is bigger, and therefore it remembers which one had the largest value, and therefore I will declare a comparison. Like I will write a lambda expression for declaring the comparison function, and I need to capture my std function, and then the comparison itself is pretty straightforward. Because we are not doing anything which requires extensive computation, where basically it's okay. In general, be mindful of how you do this, because you can see that on each comparison, the property will be computed for both elements. So it's not taking the value. It doesn't remember the value. It's just like it's recomputing it every time, and when keeping the running maximum value here, which not in every cases will be like proper what would you like to have, but here it was fine, and therefore I decided to go with it, and it just makes in the end things kind of neater and reusable. And then we, on our anagram set, we run through the set detecting maximum element with our compare function. Maximum element returns us an iterator to the pointing to the maximum element, and then in order to get the answer in terms of the number, first we dereference the iterator and then recompute its property. So you can see it's quite some recomputation here, but on the other hand, it saved me writing the same function twice. Any questions about get max property value? Then let's move on to filtering the anagram sets. And here the idea is very similar, as I can use the similar in the same in the sense of using the function that I can take the generic function and pass it as a predicate to an algorithm. Here I can do it directly, and I used copy if, which creates, in this case, creates a set. And in order to fill the set, I use dot insert, and in order to use dot insert, it's there is a helper class called std_inserter, which creates output iterator, and it feels like filter.end is a dummy argument. It may be important for when you need to insert in a vector, and it doesn't serve any purpose here in the set. Also, in a vector, I would be worried about iterator invalidation, and as it's not a problem here in the set, it's safe to use, and that's the way I fill the set. So another way would be to provide either, like, for example, make it a vector and use back inserter, which is going to use pushback, which is safe, and the second parameter would be needed, but then I would need to convert the set into a vector. And what copy if does is going through the range. It sees if the predicate returns true, it will put the element into the output iterator. Any questions about filtering the anagram set? And having this, we're basically done with our anagram set with the most words. We just I'll probably scroll a little back and remind that our property was the size of the set, and then we were comparing this anagram count, like used it as a predicate. And as I told you that things are very similar, and we're going to do very similar things for our second thing to compute. And here is the way we do it. We reuse the same function, get max property value, and filter anagram sets, but our predicate and like our compute property and our predicate parameters change. And for detecting anagram length, I found that it's a bit easier to write a freestanding function, as it goes like dot begin size, and also I've decided to put an assert there to be sure that we're not doing anything wrong. Also more for like documentation purposes. So it's gonna abort if it clearly means that I invoked something incorrectly, and I shouldn't, with all the validation I've done before, there shouldn't be something, but it's like known as famous last words of software engineer that it shouldn't happen, and therefore that's why I prefer to have an assert there. Then I pass anagram length into std function, and then pass it to get max property value. And as soon as I know max anagram length, I can also wrap it into a lambda, which is a predicate, and then I filter my anagram sets. And that's the way I've got my answer here. And we are done here with the most difficult part of the exercise. I'm gonna put these functions together, and you can see how similar they are in terms of what we are doing. The only difference is the way we like computed the property, and we're filtering the anagrams of interest. And it's pretty well localized. Still good time to ask questions about this code, if there are any. The last bit which we have to do is pretty straightforward, and we just need to put everything into our answer. And I can just, because these are the aggregate types, and I can construct them by curly braces. Both of them only have one member, one data member word set, and therefore this return, set of word sets, and therefore both of these functions return me a set of word sets, and therefore I can feed it right here and right here, and then exciting anagrams is also an aggregate type, and then we are done. And this is basically the entire exercise, and that's the material I had today. And in order to summarize it, we achieved an important thing. We now know 14 anagrams for the word alters, and we also learned about std function, and I showed you structured bindings and how they may be handy. And also we talked a bit about sorting and all of, any of, none of help algorithms which are useful to validate things in containers. As we are wrapping up with this bit, this will be a good time to ask questions about the exercise. So then, as there are no questions, we are slowly going into wrap up, and I just wanted to thank you for going through all this with me, and I hope you learned something. I just wanted to remind you where we started, and go through this list as what we've done in the course. And my intention was to show you some patterns about using the standard library and standard library containers and algorithms, and explain like some basic principles rather than going into details, and show them multiple times, so you see how principle which applies for one container can be applied to another, and how you can combine pieces together into something more complex and interesting. And we started this with switching to unit tests, and we've written a lot of unit tests, and I appreciate that people, like when sending me code, started including their tests there, and it was helpful for me for validation, and I hope it was also like helpful for you, although it was I noticed that it was a bit more inconvenience in the beginning, and I can admit that when I was starting writing tests, it was also more inconvenient than advantage. But the convenience comes with practice, and for now, I just cannot imagine how do I live without tests even for simple projects, and therefore I wanted to share this thing with you as we were doing algorithmic problems. And the next important bit about iterators and or about containers and algorithms, we figured out what are the iterators and how they work, and basically we need to make sure that we don't accidentally invalidate them and don't do any undefined behavior by misusing iterators. And we've done quite a few tricky examples and written quite a few interesting algorithms using iterators for palindromes and anagrams and basically for everything. And yeah, we done a lot of stuff related to palindromes and anagrams. And you may remember persimmon erasure exercise, after which I wasn't able to find still any persimmon in the supermarket, talking about the last bit. With another interesting bit is that we talked about lambda expressions, and I hope I was able to demonstrate you that they're quite handy in application to algorithm and for customization. And I think the hardest, the most annoying, but also kind of important bit, as it's at least one of the scariest for me in the beginning when I was learning about standard library, was figuring out custom types for associative containers, sets, and maps. And we've even written our own hash function. And basically also after the last lesson, I hope the word hash function doesn't sound like something magical to you, and you know why it's needed, how it works, and are ready to implement your own stuff when it's needed. And that's this is it for the course. I have one last piece of the additional content to suggest to you, because what we were talking about here is going to become obsolete. And I wanted to refer to the talk by our own Tristan, where he was talking about the evolution of standard library. And he gave a great talk in last CPPCon about standard library ranges, which is just better and nicer version of not exactly like algorithms, although the interface to the algorithms, I would say. And when I was preparing this course, I was realizing that as soon as this feature is implemented by the major compilers, my material is going to become obsolete. Although in the world of C++, it may take a while as it is implemented and then it is deployed and so on. So I hope it's still going to be useful. And also the things which I taught you is going to be a good foundation for further learning, as algorithmic complexity is not going anywhere. And on the other hand, I'm quite looking forward into these changes in the standard becoming available to wider audience. And in this case, when we are talking about algorithmic examples, which I used through my course, we will be able to do much more advanced things with the same amount of code, and won't need to fight like iterator matching, and we'll be able to chain algorithms easier and not copy data into arrays. And there are already some mentions of ranges in the talk by Conor Hoekstra, which I mentioned a few lessons ago. And here is just like more details in Tristan's talk of what to look forward to and what to be prepared for. And also, if you have any annoyances with standard library, you can see if these annoyances are addressed in the new version. So I will just recommend to follow up on this. And this is it for today. As usual, the last slide to remind you that we have a channel in CPP Lang Slack community, and as this is the end of this course, and with the current situation, I don't know how we're going to proceed yet, as you can expect some announcements about the isolation and the quarantine, like they said this week, and eventually it will be great to meet all of you again and get back to the nice room in the university. So we'll see how it goes further. At least I'm not going to be doing another lesson in 2 weeks. I'm going to take a little break, but that's why it's important to get on Slack. You will be able to follow the announcements and see what's going to happen next. And as the way things finish in London, they do it in a pub, and in our case, it's going to be a virtual pub. So those who are on Zoom will be able to join the pub, and I will be happy to chat more about the lessons, about your impression, and so on. Also, regarding feedback, please send it our way, and please also send what would you like to hear next. We're going to continue doing this. Just like need to see how the environment works for us. And on this note, I want to thank you again. It has been a pleasure, and I appreciate your questions. I appreciate your dedication, and I looking forward seeing you in my next lessons. And for now, so long and thank you.